Hi, welcome to Hack to Secure training on information security. In current video, we will talk about different RAID methods and related concepts. This video is part of our detailed course on data storage, network, and security. It is one of its kind and uniquely available online training course on data storage protocols, its associated technologies, and security implications. So, let's look into details about RAID and how it provides data protection in storage environment. Usual computer systems use hard disk drive as primary form of storage. Data storage in these disks is getting faster and reliable with every advancement in technology. However, there is always a risk of data loss due to disk failure. Having redundancy in data storage is an important requirement to avoid any disastrous consequences. To add on to this, as most software applications have to deal with large data files, processing or handling of these files can be slower if these are not stored appropriately and effectively. This will further impact performance of a system. In current video, we will talk about RAID and its usage to achieve reliability and performance in data storage. We will also see how it is used to provide data redundancy to protect data from hard disk failures. RAID stands for Redundant Array of Independent Disk. It is an arrangement of several hard disks acting as a single logical drive for a computer system to provide reliability and performance to data storage. Here, reliability is ensured by preventing data loss in case of disk failure by enabling easy and faster recovery of the same. In terms of data storage, performance is considered in form of ability to read and write data to a disk drive. RAID improves storage system performance by serving I/Os from multiple disks simultaneously. However, both data redundancy and performance are contradicting terms. We need to balance both based on requirement and sensitivity of data getting stored. RAID technology has now grown from theoretical concept to an industry standard and is a common implementation in today's storage arrays. Traditionally, we can implement RAID both using hardware and software methods. Let's analyze these methods one by one. Software implementation of RAID is done at operating system level and make use of host resources like CPU cycles, memories, etc. It doesn't require a dedicated hardware controller to manage the RAID array. Software RAID is also called as poor man's RAID solution due to its benefits in terms of cost and simple implementation. Administrator needs to play around software settings to manage RAID implementation without paying anything for dedicated hardware. Absence of hardware, on other hand, also limits its implementation in terms of performance, features, and compatibility. Since RAID software consumes host CPU cycles, this may impact complete system performance. Moreover, in case of large data transfers or I/Os, performance of storage device is also impacted. Adding to woes, compatibility is another concern with software RAIDs. Since it is an application, it needs to have compatibility with underlying operating system, especially with every patch or upgrades. Hardware RAID uses a specialized hardware controller either on host or on the array. In host-based implementation, controller card is installed on host or on motherboard itself. Disk drive are connected with these controllers. On the other hand, in external array-based implementation, external RAID controller act as interface between host and disks. So, here RAID controller presents storage volume to the host and host manages these volumes as physical drives. A RAID array is an enclosure containing number of disk drives and RAID controller as a supporting hardware. Here, some disks are grouped together to form a logical associations called as logical array or RAID sets or RAID groups. Controller in RAID array provides three main functions. First is management and control of disk aggregation. As RAID controller is an interface connecting host and disk, and physical disks are grouped logical manner in an array, it provides translation of I/O requests between logical disk and physical disks. And lastly, it helps in data regeneration if disk fail based on RAID configuration. Now, how data is regenerated or restored in case of RAID? We will see that in upcoming sections. Now, let's analyze some of the concepts related with RAID techniques which showcase how RAID allow data storage in disk at logical drive. Stripping, mirroring, and parity are few of the common methods. All of them differ with each other in terms of data storage method to provide data performance and redundancy. We will discuss each of them in details to lay down foundation of RAID levels. Stripping is a technique to distribute data across multiple drives and use them in parallel. So during write operation, each disk in an array is broken into units or blocks and data is distributed into these blocks simultaneously. Let a host wants to write a string, data storage network and security. On receiving request, RAID controller distribute each word across drives in array. Similarly, for read operation, each disk contributes in retrieve of data simultaneously and send to controller. We should note that this example is just for sake of understanding stripping concept. We will further look into this concept with granular details. So as we have seen in stripping, read-write heads can work simultaneously. This allows faster processing of data and therefore increase in performance with respect to scenarios where read and write operations are done from a single disk. Now let's have some in-depth detail of how stripping works. Consider a scenario with array of 6 disks. When a write I/O request comes to a logical volumes, RAID controller helps to distribute all data to physical disk. Here, each disk is divided in small blocks, such as block 1 is on disk 1, block 2 is on disk 2, block 3 is on disk 3, and so on. Here, as block sequence forms a series of strips across the disk, hence this arrangement is referred as stripping. Data is distributed in a strip at a time, means each bit of data is stored in a block of strip, next bit got to another block on same strip and so on. Once all blocks are filled in a strip, filling of another strip starts. Disk in strip mode provides high performance or high speed as logical drive exposed to controller adds up to the speed of all physical drives under it. Say, if a logical drive or array contains 6 disks that are capable of handling 100 I/O per second, then capability of logical drive will be 600 I/O per second. Since all disks in a volume are getting utilized, disk using stripping methods offer zero capacity loss or overhead. However, stripping techniques provide zero fault tolerance due to absence of redundancy in method. So, stripping alone does not provide any data protection, but when combined with other methods, this drawback can be overcome. In upcoming sections, we will see how stripping method can be utilized along with other methods to provide RAID configurations. Strip size or strip depth or a chunk is number of blocks in a strip. It also shows maximum amount of data that can be written to or read from a single block. Stripe is formed from a row of chunks presented from all physical size. Mathematically, stripe size is multiplication of chunk size and number of disks in RAID set. For example, if we have a RAID set of 6 disks with each chunk of 16 KB, then strip size will be 96 KB. Strip width is number of drives in a RAID set. Since stripping allows data to be stored in parallel to all disks in a logical array, chunk size should be adjusted based on I/O size. In case I/O size is large, we should use smaller chunk to distribute data faster. On the other hand, if I/O size is small, chunk size can be increased. So thumb rule is larger the I/O size, smaller the chunk. Smaller the I/O size, larger the chunk. Mirroring technique makes same data to be stored on two different disk drives. So copy of data is maintained to ensure redundancy in case of data loss. Here, two physical drives are placed in a mirror pair so that data getting stored will be replicated or copied to another in parallel. In mirroring, logical disks have two mirror pair of physical disks providing medium to high performance irrespective of size of IOs. For write operation, data is written on two drives, hence write performance is impacted by this. It can be optimized based on methods used to mirror data. One can choose to write data in parallel to both disks or can write to one and let it replicate to another in parallel or after some interval. During RAID operation, performance is good as requests can be serviced from both disks. Now, since equal amount of duplicate data present in logical volume, capacity of logical drive is decreased by 50%. For example, if an array contains two physical drives of capacity 1 TB each, capacity of logical drive exposed to controller will be 1 TB only. In case of fault tolerance, mirroring method can withstand a failure of one drive. So if we replace failed drive with a fresh one, mirrored pair of failed drive can be replicated its data and fault tolerance will be restored. Parity is a redundancy method that ensures data protection by checking errors, ensuring data integrity, and recovering data in a binary system. Calculation of parity bit is done by RAID controller. These parity bits can be stored either on an independent drive that is placed separately with existing disk drive or on one of existing drive that can be dedicated for parity storage. We can even distribute parity bit across all drive in a RAID set. Parity can be either even or odd, and it depends on user implementation and usage. Both types provide same results. In this lecture, we will use even parity in our examples. Even parity is implemented to ensure that there is an even number of ones in a row of data. Consider a RAID set of 5 disks. Here, last disk is dedicated to store parity bit. In 5-disk RAID set, 4 disks are used to store data and 1 disk for parity. In this scenario, incoming data is divided in sets of 4 bit each. Each of 4 bit is stored in a block of each disk and parity is calculated to ensure even number of ones are present in each block strip. If bits in a data set are all 0, parity bit will be 0. If data set contain odd number of ones, parity bit will be 1 to make it even, and at last, if a data set contain even number of bits, parity bit will be again 0. Now in case of disk failure or data loss, we can always calculate lost data in a disk using parity bit. Here, parity bit can provide measure to know which data bit is lost. Single parity is used to recover data from single drive failure. Similarly, we can use double parity to recover data from 2 drives. Overall, unlike mirroring, where we have capacity loss of 50%, using parity we have small capacity loss to store parity data, but in return, we have effective data redundancy. Now, let's look into arrangements and method used by disk drive to store data. These different configurations are also known as RAID levels. Stripping, mirroring, and parity techniques are used either independently or in combination with different RAID levels. Depending upon requirement in terms of data redundancy, performance, and cost, one can choose RAID level. Starting on different RAID levels, first in queue is RAID level 0 or RAID 0. RAID level 0 uses data stripping method where data is stripped across all the disks with a RAID set. Minimum of 2 drives are required to distribute data in strips. To read data, all strips are put back together by the controller. So as number of drives in RAID set increases, performance improves accordingly. RAID 0 is a good option for applications that need high I/O throughout, as more data can be read and write simultaneously. Like in case of video streaming, video editors working with very large files can use RAID 0 while editing multiple streams of video for optimal playback and performance. However, technically speaking, RAID 0 is not a RAID in itself and it does not provide any data redundancy and high availability. So in case of data failure, data can't be recovered or restored back. Due to lack of any data protection, RAID 0 is not used as a single storage backup solution on critical systems. So we have seen RAID 0 is actually not a RAID configuration due to absence of any redundancy provided by it. Another RAID configuration is RAID level 1 or RAID 1. It uses data mirroring technique to provide data redundancy and high availability. In RAID 1, every disk is arranged with its mirrored set and data is written on both the disk. This provides low write speed. However, this performance impact can be improved by writing data on one disk and replicating to another in parallel. This improves write speed to some extent, as now instead of two disks, data is written on one. But replication to another disk may not be real-time and consumes host CPU. On the other hand, as two disks are available in parallel for read heads to extract data, read speed is quite good. Data mirroring in RAID 1 is transparent to the host. So during disk failure, RAID controller has readily available disk to continue its operation and zero data loss is encountered. Once malformed disk is replaced, data is replicated to ensure smooth operations. It is best suited for applications which require high availability and performance. Apart from low write speed, cost is another constraint in RAID 1 implementation. Here, data is mirrored, so minimum of 2 drives are required to implement this technique, and out of which only one is used for actual data storage. RAID 1 suffers from capacity loss of 50%. We have seen RAID 0 providing high performance but no data redundancy, while RAID 1 is good to ensure data redundancy but lags in performance and is high on pocket. Nested RAID is another RAID implementation where we combine both RAID 0 and 1 architecture. In other words, it uses both stripping and mirroring technique to get both data redundancy and performance. Usually, nested RAID require minimum 4 and an even number of disks. We can combine RAID 0 and RAID 1 in two ways. First is RAID 1 plus 0 or RAID 1 0, where data is first mirrored and then stripped. Another method is RAID 0 plus 1 or RAID 0 1, where data is first stripped and then mirrored. Confused? Let's understand them better. Under RAID 1.0 implementation, data is stripped in mirrored pair format. To understand it better, let's consider RAID set of 8 disks arranged in a 4 set of pairs. Now every pair is combined as a logical disk. This logical disk is presented to a RAID controller, which is an independent disk. In RAID 1.0 implementation, RAID controller distribute data from logical volume in these 4 logical disks in stripped manner, like done in RAID 0 implementation. Since each of these logical disks contain 2 disks arranged as mirror to each other, so originally data in physical disk under each logical disk is distributed in mirrored manner. From figure, we can see how data is stored in both physical disk under a logical disk. So this is just to provide understanding of data distribution in RAID 1.0 implementation. Originally, we can see how data is stored in stripped mirror format. In other words, we can also say that data is first mirrored and then both copy of data are stripped across multiple disk drive pairs in RAID set. So in terms of performance, RAID 1.0 will have good read performance as data is stored in stripped format, and also 2 mirrored disk provides measures to overcome read overheads. However, this implementation experiences a poor write performance as data has to be either written twice or needs to be replicated to mirrored pair in parallel. This makes RAID 1.0 implementation good for small, random, and write-intensive IOs. In terms of data redundancy, RAID 1.0 provides fault tolerance of up to 1 disk failure in a mirrored set and faster data recovery, as data just needs to be replicated from mirrored pair. However, if both disks in a mirrored set are lost, data cannot be restored. RAID 1.0 suffers from at least 50% capacity loss due to mirroring of data. Another type of nested RAID configuration is RAID 0.1 or RAID 0 plus 1. It is implemented as reverse process of RAID 1.0. Here, mirrored strip solution is provided, means data is stripped first and then entire strip is mirrored. To understand it better, Let's consider RAID set of 8 disks arranged in a 2 groups of 4 disks each. Now both groups are treated as logical disks and are configured as mirror set of each other. This logical disk is presented to a RAID controller, which treats it as an independent disk and store data in physical disk in stripped format. As both logical group of disks are mirror of each other, same data will be mirrored in other group of disk. Originally, it will look like data strip are mirrored or data is stored in mirrored strip format. RAID 01 configuration provides better write performance with respect to RAID 10. Since data is initially stripped and then mirrored or copied, write heads can perform it in a much faster manner. Just like RAID 10, RAID 01 also has good read performance due to presence of 2 disks having same data to overcome any read overheads. For data redundancy, RAID 01 provides fault tolerance at strip level. If one drive fails, then entire strip is faulted, which can be replaced with that of another group of disks. A recover operation copies entire strip, copying data from each other in healthy strip to an equivalent disk in the failed strip. This in turn may cause increased I/O load. Just like RAID 10, RAID 01 also suffers from at least 50% capacity loss due to mirroring of data. RAID 3 and RAID 4 are another in-queue for RAID implementation. Both RAID types make use of dedicated parity disk to provide fault tolerance. As discussed earlier in parity technique, parity information is stored on a dedicated drive, so data can be recovered if a drive fails in a RAID set. We need minimum of 3 drives or disks to implement RAID 3 and 4 level. Only difference between both RAID types in terms of how parity bit is used. RAID 3 uses byte level parity, while RAID 4 uses block level parity. From performance point of view, both RAID types uses data storage in stripped format. However, RAID 3 is not recommended for intensive use of non-sequential file reads. It is often used for long sequential files like video files. On the other hand, RAID 4 store parity at block level. This makes data disks to be accessed independently, so specific data elements can be read or written on a single disk without reading or writing an entire strip. Due to presence of parity blocks in each strip, both RAID types provide data redundancy in case of a single disk failure. RAID 5 implementation is just like that of RAID 4, with only difference in terms of parity storage. RAID 5 implements block-based rotating parity or distributed parity. Here, parity is distributed across all disks to overcome write overhead of a dedicated parity disk. In a 5-disk RAID 5 implementation, parity is rotated to each disk in a strip starting from end. So, first parity will be stored in a block of disk 5, then for next strip, parity is stored in a block of disk 4, then on disk 3, disk 2, and so on. This parity distribution make RAID 5 good for random read-intensive I/O. Write performance is average as small block random writes. Since parity is distributed across disk, it doesn't allow RAID controller to readily write data to blocks present in back of parity block. So, full strip write is not possible. Controller has to calculate parity before proceeding to other block set. In terms of fault tolerance, RAID 5 supports data redundancy of one disk failure. We can always take out any one faulty disk in implementation and replace it easily to recover data sets. Overall, although distributed, parity disk storage size is equal to one disk size in complete RAID set. So mathematically, capacity overhead is percentage of single disk contribution on complete RAID set. For example, for RAID set of 5 disks, capacity overhead will be almost 20%. RAID 6 works like RAID 5 but with 2 distributed parity blocks in each strip. So this makes it to survive up to 2 disk failure in a RAID set. In a 5-disk RAID 6 implementation, 2 parity blocks are rotated to each disk in a single strip starting from end. So first two parity will be stored in a block of disk 4 and disk 5. Then for next strip, another two parity will be stored in a block of disk 3 and disk 4, and then on disk 2 and disk 3, and so on. In terms of performance, like RAID 5, RAID 6 has good read performance due to stripping method used for data storage. However, it experiences bad write performance, even poorer than RAID 5 due to presence of two parity blocks. Main advantage of RAID 6 is in data redundancy provided. RAID set with disk configured per RAID 6 configuration can survive up to 2 disk failures and provides high level of data resiliency. This is the highest from all the RAID implementation discussed till now. However, due to presence of two parity blocks, rebuild operation takes longer than RAID 5. Adding to woes, further capacity overhead is more than that of RAID 5 due to presence of two parity bits in each strip. So, technically, each RAID set requires 2 disks to store parity. Mathematically, for RAID set of 5 disks, capacity overhead is almost 40%. It is a concept of having a spare drives in a system which can be automatically replaced with failed drives. This increases data recovery time in a system and fault tolerance level is maintained. Having active hot spares also reduces criticality of having administrator availability every time. Especially on weekends or public holidays, system can withstand any critical drive failure without any compromise in fault tolerance and compliance. Hot sparing can be done in both physical and virtual form. In physical hot spare, a dedicated physical drive is introduced in a RAID array which may be actively running and can readily replace malformed drive. Suppose there is a RAID set of 6 physical disks of 500 GB each. In this case, one disk can be dedicated as a hot spare. This means RAID set to lose capacity and performance of one disk, but it adds redundancy to RAID set. We can also introduce virtual or distributed hot spares where an equivalent amount of space is dedicated in each RAID set to recover from a failed drive. This is quite useful in terms of both performance and data recovery time. Here, during normal operation, performance of all drives will be accounted. In case of drive failure, all remaining drives will participate evenly for data recovery. Suppose there is a RAID set of 6 physical disks of 500 GB each. In case of virtual hot sparing, a slice or a portion of each disk is dedicated as space. Say, a slice of 100 GB is dedicated from each disk, so here total of 600 GB will be dedicated as virtual spare without impacting much on capacity and performance. So here we finish our lecture on RAID technology and have seen how different RAID implementation ensures data redundancy in an array. Now let's quickly summarize all concepts discussed in this video. RAID stands for Redundant Array of Independent Disk. Its implementation ensures reliability and performance of data storage. RAID controller is heart of RAID concepts, which controls all data distribution in physical disk. It can be a software or can be implemented as independent hardware. Stripping technique distributes data across multiple disks in parallel. RAID 0 implementation is based on stripping method. It doesn't provide any redundancy but ensures high performance. In mirroring technique, data is copied to another disk in parallel. So, a mirrored copy of disk is always present. RAID 1 implementation is based on mirroring method. It provides fault tolerance to sustain one disk failure in RAID set but add up to cost and poor write performance along with capacity loss of 50%. RAID 1.0 and RAID 0.1 are nested RAIDs making use of both stripping and mirroring method. In RAID 1.0, data is first mirrored and then stripped, while in RAID 0.1 data is first stripped and then mirrored. Both RAID types provide good read but moderate write performance with capacity loss of 50%. Parity methods provide data redundancy by error checking and data recovery. RAID 3, 4, 5, and 6 uses parity method. RAID 3 uses single parity at byte level, while RAID 4 uses it at block level. RAID 5 make use of parity in distributed manner in all disks present in RAID set, while RAID 6 uses double parity to provide redundancy of sustaining two disk failure in a RAID set. Both RAID 5 and 6 have poor write performance. Hot sparing of disk in a RAID set is used to automatically replace failed disk to minimize downtime. In physical hot spare, a dedicated disk is reserved as spare, while in virtual hot spare, a portion or slice of disk is dedicated as spare. So, here we conclude our lecture on data protection with RAID. Don't forget to take a quiz on RAID before moving to next lecture. It will help you to brush up your learnings. Also, feel free to consult if you have any query or if you want to deep dive on any topic discussed in this lecture. Hope this video has been helpful for you to learn basics of RAID. However, if you are interested in our complete course on data storage network and security and want to learn more about the detailed topics like storage devices, protocols like fiber channel, iSCSI, NAS, FCOE, data backup and redundancy, storage protocol, security and many more, do visit us at www.training.hacktosecure.com. Also, don't forget to look for exclusive offers and discount coupons provided in descriptions of this course. Thank you for your interest.